Hello guys, today we are going to discuss the paper towards retrieval-augmented architectures for image captioning published in ACM journals, and it was our mentor was Chaitanya Dubey and instructor is Mayank Singh. So coming to introduction, image captioning is nothing but for an image we we use an LLM to generate a caption automatically. It's not just LLM, but we can also manually generate captions. So that is what is image captioning is. But it is widely used in multimedia systems accessibility. It can also help visually impaired users, and it can be used in search and recommendation systems. And for this, but challenges include visual textual modalities, as we can't the algorithms can't directly understand the image itself. So uh, the main challenge here would be to bring the visual and textual modalities together, and it also need accurate object recognition and fluent language generation to automate this. So coming to the problem statement, there are a lot of models currently for image captioning, but right now the current limitations for image captioning are it is very dependent on memorization. It needs to be trained on a very large amount of data to have more context, and using larger models will also have higher cost, slower training, and scalability issues also. And it can't very well describe the novel objects present in the train if they are not present in the training. Like if your Eiffel Tower is not there in the training dataset, it won't generate the Eiffel Tower as a Eiffel Tower. It will just some steel monument. That's it. And it also produces generic and biased captions. uh, they depend on the data set, so it's very data set relevant. And what the authors proposed in this paper is to use a retrieval augmented approach to use external memory and retrieve the nearest, like most related captions using kNN of image text space to separate language modeling from memorization. And they also propose two variants. We'll see those in the next slides. And this scalable solution also improves accuracy. It also covers novel object coverage and reduce reliance on memorization. Coming to next, and in this paper we use three datasets. One is MS COCO, which has 118,000 images. One is nocaps dataset, 15,000 images, and CC3M images, which is 3 million images. And this CC3M images uses a auto-generated captions with blip. Okay, so coming to the literature survey of this image captioning, uh, in 2000s, image captioning was heavily template based. Like to an image, there will be some predefined templates which will be automatically filled out based on the generated whatever object recognition or other techniques. From 2014, we have the CNN plus RNN techniques, which can be used to automatically fill out without using any templates. And from 2016, we started using transformers. Until now, we are still using transformers. And the novelty in this paper is to use the retrieval augmentation that came in NLP in image captioning. So that is the novelty in this paper. Uh, so comparing the normal image captioning model and this REG model proposed in this paper will be like in normal image captioning, you give an image and it passes to a visual encoder which encodes the image in some form of vector, which will then be given to standard captioner, which generates a caption. This is the normal image captioning model process. So what the authors added in this paper is that normally we give the image to the image visual encoder, that will be the same, but along with standard captioner, we also give this visual encoding to an external memory, which retrieves the nearest top k captions from an external memory using some kNN or other methods. And we pass these top k retrieved captions along with the visual encoding to this retrieval-augmented captioner, which generates the final caption. You can also see the difference in the captions generated between a normal and uh, RAG augmented caption. So you can also observe that there is more context present in this RAG augmented. Okay, so there are four key components in this architecture. One is clip visual encoder, which encodes the image. Then transformer visual encoder also does the same. External memory storing which stores the image caption pairs, and transformer decoder which generates the image caption, which yeah. And architecture integrates the retrieving from the sectional database to improve the accuracy. So, this clip visual encoder is modified by removing the attention pooling layer and using custom pooling functions. And external memory maps images to the vectors. And we also use the similarity calculation embedding transpose embedding too. And we use kNN to look up and retrieve the captions based on the similarity. Okay. So this transform visual encoder takes grid feature vectors from the image as an input, and standard transformer layers have self-attention plus feed-forward layers, and transformer decoder takes the sequence of tokens from the ground truth caption and also the top K retrieved captions and predicts a shifted version of the caption. So there are two types of architectures proposed for this retrieval augmentation. One is RATS and RATX. We'll see what they are in the next slides. But RATS is basically self and X is for cross. So in RATS architecture, we take this top K retrieved captions and use them as a prefix to the other input. And we also, before using them, we have to process the words by removing stop words, duplicates for unique tokens, and other processing techniques. And we have to segment embeddings and mask self and use masker self, and it uses masker self attention. So whereas RATX, instead of directly using them as a prefix, passes the stop K retrieved caption through an encoder which encodes those to a separate external memory encoder which encodes those captions and give it to a kNN augmented attention layer. And we use this kNN augmented attention layer and masker self attention layer and combine them with a learnable gate to pass it through the cross attention layer, which passes this to the final, which gives the final caption. So the main difference in between RATS and RATX is in this learnable gate. In this cross attention there is this learnable gate, whereas in RATS we directly use the top character captions as a prefix after processing. Uh, Coming to the loss function used in this paper, for training we use the cross entropy loss and then fine tune it with reinforcement learning to directly optimize with metrics like CIDER. And this is the loss function. This is the loss function used in this paper. So in this, the key terms are K is the sample words at each step, and RYI is the reward here CIDER for each sentence YI, and B is the average reward baseline calculated by computing the mean of rewards. And the significance of baseline is to reduce the variance of gradient estimate. And this gradient of log P YI, this tells us the direction in which the parameters need to be adjusted, and the R minus B tells us how the model is performing compared to how the caption is generated compared to the baseline. And this negative sign is to minimize, like normally cross entropy loss is this positive value, so for loss we have to minimize it, so we added this negative sign. So coming to the results in this paper, so here we can see that increasing the number of retrieved captions also increases the maximum scores that we get. And you can also observe the baseline and the improvement in using the RAG. Here we only got 25.5, but here we got 59 using RAG. Similarly, using five captions, uh, we got 74.1 using Oracle, and here we got 78.5. Like here also 40.9 and 46.5, 65.5 and 72.3. So using external database is really useful in increasing the context, and this paper is useful. The same comparison here also, but with 20 and 40 you can observe that using 20 is much higher than 5 or 10, and using 40 is even better. So, and everything else is still same, improving. Like here we only got 51.8 using the original, and using our RAG approach we got 81.9. So you can also compare the architecture RATS and RATX. Here we only got 78.5 and here we got 78.9 using cross attention, but that might be just some statistical errors, so we can't say. But overall, this is the comparison between the two architectures, and this is also the same kind of comparison. There is not much, like you can see the improvement with this ablation study kind of. Mm. And these are the examples generated. Like this is the caption that is generated using these retrieval captions. Yeah. You can see that a bowl of salad with carrots and lettuce. You can see that it took the context from all these retrieved captions and used it to generate the caption. So going to the next slide. Similarly with nocaps dataset also. Transformer without external memory, a birthday cake with candles on top of it. And using RATS, a person is holding a birthday card with a cell phone. And RATX, a person lighting candles on a birthday cake. We can see the improvement in this also. A plate of food with carrots and potatoes on it, a plate of food with carrots and beets on it, a plate of carrots, mashed potatoes, and a cup of water. They added this context. Similarly, there are some improvements. So coming to the future work, right now there is one very important limitation in this paper, which is that inference time is very high, because even in inference we have to perform retrieval, so that is much higher compared to normal architectures. So in future, for future work, we can develop more sophisticated visual semantic embeddings to improve the relevance of retrieved captions, and we can also enhance the external memory database to improve the quality of generation. So we so we can explore using the more large, diverse, and higher quality external memory sources to further boost the captioning quality and semantic richness. And we can also scale this retrieval process, like others mentioned techniques like PCA and vector quantization to scale the larger datasets, but they didn't implement them for the simplicity sake. So for future work, we can just investigate and apply these techniques to make RAG more viable for web scale external memories. And we can also make this an end-to-end trainable retrievers. Uh, Here the kNN index is static and it's not really updated during the training. So in future we can explore methods to make retrieval component learnable, to make the gradients flow back from captioning model to fine tune the retrieval embedding for this specific task. So as for novelty that can be extended from the existing work, so one is the multilingual. We can use this paper is only English centric, and we can use this paper to generate quality image captioning for low resource languages like Indian languages which doesn't have very large data available, and we can use this for 10 to 11 Indic languages by building new multilingual knowledge base and adapting the model for cross-lingual retrieval generation. And we can also use hybrid VLM RAG architecture and comparison. Like we can use pre-trained VLM like Chitrad. They are strongly generative, but they lack external memory. So we can use this as a base, uh, and use and build a RAG approach on top of this, which we think is much better. So basically, this Chitrad stack combines the VLM reasoning with retrieval based grounding and first quantitative analysis of RAG impact on, and we can also present the first quantitative analysis of RAG's impact on image captioning against the Chitrad baseline. So our experimental plan currently is that we will do data curation. We will translate the MS COCO image captioning to 10 or 11 Indic languages, and we aggregate the existing Indic languages dataset for image captioning from public sources like Kaggle and other sources, and we build a multilingual external memory We encode all images using clip visual encoder, encode all multilingual captions using multilingual sentence transformer, and then index these embeddings into FARs or a similar vector database for efficient kNN search. After this, model training and evaluation. Uh, we plan to implement the baseline Chitrat VLM without the RAG component and propose it VLM with RAG component, multilingual part. And we train both these models on the curated multilingual dataset until convergence. So here this Chitrat VLM is the baseline and this hybrid architecture is what we are proposing. And for evaluation, we measure performance using the standard techniques Blue, Meteor, or CIDER, SPICE for each language. And for qualitative, we also conduct a comparative analysis of generated captions, focusing on accuracy and relevance. Okay, so that